In this video, I'd like to talk a little bit more about our time-varying quantities with the goal of explaining what this RMS value is that we've mentioned before. So in AC circuits, we have this convention that our time-varying values we write with lowercase variables, right? So our time-dependent current, like I as a function of time, we write like this. Our V as a function of time, we write like this. And we know roughly what these functions look like, right? Maybe our current is some cosine of omega t, where omega is our angular frequency, 2 pi times f, plus some phase, and out front here there is an amplitude that we write as a capital I, and we could call that I naught, or we could call it I max. Either of those are going to make sense for us. Let's call our amplitudes I naught just for now. I think that'll work. So our current might look something like this. V, I'm not going to write down right now. It's going to be V naught times, capital V naught times some oscillating thing that doesn't have to be cosine of omega t plus phi. It could be cosine of omega t plus a different phi, or it could be the same phi if we're talking about the two being in phase. Anyway, so cosine of something. So we have these similar looking things. Capital letters here are denoting the amplitudes. Okay, so let's talk now about power dissipation. So if we do have a resistor, let's imagine we have a very simple circuit. Okay, we have an AC voltage source going into a resistor. If this is true, then we know that these two are in phase, and we can write cosine of omega t plus phi. Those two are going to be the same. So in this case, we have this current that is, well, sometimes going clockwise, sometimes going counterclockwise, passing back and forth through our resistor. And the power dissipated by the resistor is going to be the current through the resistor times, well, this is what we learned in like DC circuits, the current through the resistor times the voltage across the resistor. But now, of course, these values are varying in time. So really what we end up with here is we have some instantaneous power. So the power dissipated at time t is equal to the current at time t times the voltage at time t. And this is true at any point in time. We can have points in time when our power is larger and points in time when our power dissipated is smaller. So let's draw a little graph here. We know what these look like. I don't need to keep those up. So if we have something like this, where our voltage is this cosine, I can draw a graph of what our power looks like. And it turns out that if we have if we're multiplying I times V, we're going to get a cosine squared. Remember also, we have another equation for power for resistors, like V squared over R or I squared times R. In any of these cases, we're going to end up with a cosine times a cosine, right? And so our power function, if this is our voltage, say, our instantaneous power is going to look like this. It's going to go down to 0, and then it's going to go back up, and then it's going to go back down to 0, and then it's going to go back up. It turns out that cosine squared, this is just a math thing, this doesn't have anything to do with the physics right away. Cosine squared function is equal to a cosine function that is twice the frequency and shifted up, so it's only between 0 and 1, or 0 and the max. So maybe I'll write this in a more explicit way. So if cosine goes from -1 to 1 at frequency omega, then cosine squared goes from 0 to 1 at frequency 2 omega. Okay, and that's what I have drawn here. So our peak power we can figure out from whatever our peak voltage is, right? So P max here is going to be V squared over R, where V is now V naught squared over R, or we could write that as I naught squared times R. Either of these are going to give us the same maximum power. But very often, we're not so interested in the maximum power as we are in how much power we're dissipating over long periods of time. Remember, this oscillation in a circuit might be happening 60 times a second, it might be happening 1,000,000 times a second. And generally what we're interested in with power dissipation is how the temperature of things change, and that happens over much longer time scales, maybe fractions of a second, but most likely at least a few seconds. So when we're talking about power dissipation, we're talking about averaging over many cycles of this oscillation. So because of that, it's far more likely the case that we're interested in the average power rather than the peak power. So if we are interested in the average power, well, you can see from this graph, if our power is oscillating like this red line up and down, and this is a cosine, so it's nicely symmetric, our average power is just a line going through the middle of this red line. So our average power is 1/2 the maximum power for this sinusoidally oscillating thing. If you don't believe me, you can integrate the red function and prove it to yourself, but you can also look this up and trust that is the case. So the average power is 1/2 the max power for these sinusoidal functions. And again, this is assuming that we're averaging over many cycles. Okay, so what the heck does this have to do with this RMS voltage business? Okay, so here's what I will now point out. So if we only record these peak values, if we only have V0 and I0, because these are the things that we're measuring, if we want to calculate a power using those, when we use these, V squared over R or I squared R, we always get the max power. And we could remember to divide by 2, but it turns out to be very, very convenient to define a new way of measuring the amplitude. So instead of talking about this peak value, right? So instead of talking about the maximum voltage that you have, which is the same as the distance between 0 and the minimum voltage, right? This distance is the same as that. Those are both V0. So instead of measuring your functions in terms of that, we measure them with a new quantity called the RMS voltage. We can remember all that, I think. So the RMS voltage, that's the root mean square, so that is the square root of the mean of the square. Square root of the average of whatever our quantity is squared. So in this case, squaring our voltage is going to give us, squaring this green graph gives us a graph that looks like the red graph. The units are not going to be power if it's just V squared, but it'll look something like that. We take the average, which gives us this purple line, and then we take the square root of that, which gives us some number of volts, right? This still gives us units of volts. Now, what's cool about this is these RMS values, when we multiply them together to find a power, or when we square them to find a power, they give us exactly the average power. So RMS values give P average the same way that our maximum values give P max. So this is why these are useful, and this is why these are used very often in describing AC circuits in real life. So, for example, like the voltage at wall outlets is 60 hertz, so it's oscillating, positive or negative 60 times a second, and it is spec'd at 120 volts. You have people always talk about, well, sometimes people talk about 110 volts because that's an older standard, but 120 volts is what it's spec'd at. And that leads to some nice, without thinking too much about the fact that it's AC, you can do back of the envelope calculations like say, oh, well, it's 120 volts at 1 amp, which gives me, volts times amps is watts. So that's 120 watts of power for my 1 amp current flowing to my washing machine or whatever. But now that we know what's going on here, that voltage must be a a RMS voltage because we're getting an average power. We're not saying, oh, well, at this moment in time, the washer is dissipating 120 watts, but at this point, it's dissipating a smaller amount of power and so on. So the power you get from that little back of the envelope calculation is the actual average power, and that's because that 120 volts is a RMS value. And if you go and measure the power in a wall outlet, it actually oscillates up and down between plus and minus 170, roughly. So we'll talk about where that number comes from in just a second. Okay, so from this average, you can see that this average value, so for the power, I'll just redraw the graph for voltage, that'll be easier. So if we have this voltage graph still, so this is our V of t. So our voltage squared looks like this one. This is V squared as a function of time. So the average of that is going to be 1/2 of this maximum value squared. So the average, let's see if we can write this in math language. The average of V squared, that is going to be equal to 1/2 of the maximum value V naught squared. So the square root of the average of this squared thing, the square root of the average of V squared is going to be equal to the square root of this thing on the right, which is the square root of 1/2 times the square root of V naught squared, which is V naught. Okay, so all of this is to say that our RMS voltage, which is this thing on the left, that is equal to 1/2 times our maximum voltage, which I will just write as V max to remind us that that is what V naught means here. Now, this assumed that everything's oscillating sinusoidally. We will later talk about signals that are not sine waves, and so I will specify that this is true for a sine wave. So it's this factor of 1/2. 1/2, in case you don't remember, that is the sine or cosine of 45 degrees. That is 0.707 with some other digits, I guess, approximately equal to. So the RMS value we get is about 70% of the peak value, and this is the value that will give us the average power when we plug it into other equations. Okay. So hopefully that goes to explain why these RMS things are useful and why they pop up so many places. Okay, since we're talking about power, we've assumed here that this is all for a resistor, but all of these same assumptions are going to work for any current and any voltage, whether they're, so if it's for something other than a resistor, they might not be in phase with each other. We just have to make one small modification, and that is called the power factor. And here's the idea behind this. If I and V are in phase, we just, this is what we saw, like for a resistor, all that stuff we just said was true, and we get, our average power is equal to V squared over R, or actually, let's keep this general. Let's say it's I times V, where these are the RMS values. Okay, if these are not in phase, there must be an angular difference between them, right? We have our current function and our voltage function, and we can figure out what this difference between them is in terms of some phase theta or phi or whatever we want to call that angle. So if this is true, we can write our average power like this. We can write it as V naught, I naught, so these are our max values, over 2 times the cosine of theta, where theta is now the phase difference between I and V. And again, if we're talking about, assuming we're talking about sine waves, we can also rewrite this as IRMS VRMS times the cosine of theta also, right? Because if each of these are different by a factor of the square root of 2, then these two things are the same. So this cosine is called the power factor. And this tells us how much our power is changed by the fact that these things are out of phase. Okay, so two extreme cases. If the two things are in phase, like for a resistor, theta is 0, cosine of 0 is 1, and we get back our equation from before. If the two are 90 degrees out of phase, which is what we would have for a ideal capacitor or an ideal inductor, then we're taking the cosine of 90 degrees. Cosine of 90 degrees is 0, and so 0 times this stuff gives us 0 average power being dissipated in our ideal capacitor or our ideal inductor, which makes sense. Those things in our ideal analysis, those things conserve energy. They can store energy, but then they give it back to the circuit as the state oscillates back and forth. So yeah, that's consistent with what we expect. If we have some angle in between 0 and 90 degrees, well, then we're dissipating some power, but it is not, it's something less than I times V by an amount equal to whatever that power factor is.